Next thing we want to look at is Dalton's law of partial pressures. Dalton's law of partial pressures deals with mixtures of gases such as the atmosphere. We think the atmosphere all around us is a mixture of a number of gases including oxygen, hydrogen, nitrogen, carbon dioxide, water vapor, and a whole number of other gases. Dalton proposed the idea that each gas contributes to the total pressure of that gas. We can express that idea as the total pressure is the sum of the pressure of each individual gas that makes up the mixture. So this seems pretty straightforward. If you have three gases, the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 will be the total pressure. And however many gases you have, you add them all together to get your total pressure. Now, we can also go in reverse, knowing the total pressure, and using it to find out the partial pressure of one of the individual gases. We will use this during the butane lab. Anytime we collect gas, we usually collect it over water. And if we collect a gas over water, that gas contains both the gas and water vapor, or water in the gas form. So we need to separate the pressure of the gas from the pressure of the water in the mixture. When we are doing this, we want to look at the mole ratio of those gases, and we can also look at it from that formula we just were showing on the previous screen. So here are some examples. A mixture of neon and argon gases exerts a total pressure of 2.39. What is the partial pressure of neon alone is 1.84 atmospheres? What is the partial pressure of argon? So in this case, our pressure total will be the pressure of neon plus the pressure of argon. So 2.39 equals the pressure of neon, 1.84, plus the pressure of argon. So the pressure of argon will be 2.39 minus 1.84. So the pressure of argon will be 0.55 atmospheres. So that's a pretty straightforward case. Now, a 450 centimeter cube sample of hydrogen is collected over water at 12 degrees Celsius. The vapor pressure is 12 degrees Celsius is 10.52 millimeters of mercury. Pressure of hydrogen and water together is 78.5 kilopascals. What is the pressure of the dry hydrogen gas? So once again, total pressure in this case will be the pressure of the hydrogen plus the pressure of the water. So we've got the total pressure, 78.5 kilopascals. Pressure of hydrogen, we need to convert to kilopascals, so 10.52 millimeters of mercury. There's 101.325 kilopascals for every 760 millimeters of mercury. So we get 1.40 kilopascals. So the pressure of hydrogen plus 1.40 kilopascals. So we subtract 78.5 minus 1.40, and we get 77.1. So the pressure of hydrogen here would be 77.1 kilopascals. You know from just your everyday experience that water evaporates and forms a gas more at higher temperatures than at lower temperatures, and the water vapor pressure will give us an idea of the pressure of that water in a gas form at every temperature. You can look those up in a chart on the internet to find the pressure of water at any temperature. Okay, a tank contains 480 grams of oxygen and 80 grams of helium at a total pressure of 7 atmospheres. We want the partial pressure of oxygen. Another version of this is that we can do the pressure of a gas is equal to the percentage of that gas times the total pressure. Just a basic way of rethinking that equation. So if we can figure out the percentage of the gas that's made up of oxygen, we'll therefore be able to multiply that by the 7 and get the pressure of oxygen. To do that, we need to convert each of these into moles, because we can't do a ratio without being in moles, a common unit. So 1 mole O2 over 32 grams get 15 moles of oxygen. You do the same thing with helium. One mole of helium, and helium is 4.00 grams per mole. You get 20 moles of helium. So our total is 35 moles of gas. So the percentage of oxygen will be 15 divided by 35. 0.43%, or 0.43, or 43%. Multiply by 100, you get 43%. So in this case, to get our pressure, the pressure of oxygen will be 0.43, the percentage of oxygen, times 7, which is 3.01 atmospheres. So in other ways, you can figure out the percentage of the mixture by moles that's made up of each gas, and multiply that by the total pressure, and you'll get the pressure of the individual gas. So there are a couple of example problems using Dalton's law of partial pressures. We'll run into this most often when looking at lab data where we collected gas over water and have to subtract out the vapor pressure of water from the total pressure to find the pressure of the dry gas.